Welcome back, students. Again, this is Jayalakshmi. Now we are going to discuss about the next topic in our next video is differential amplifier. I hope that you have understood that previous topics we have discussed in the second unit. This is the final topic and important topic in the second unit. You can definitely you can expect one question from this differential amplifier. It may be either about that configurations or general operation of a differential amplifier, or you may be asked to write that AC analysis of the differential amplifier, or you may asked to obtain that common mode rejection of a differential amplifier, or you may be asked to obtain the DC transfer characteristics of a differential amplifier. So there is more possibilities of questions. Part B questions may be asked from this part, so be ready to listen it. All the best. What is an amplifier? First, if you know that one, an electronic device for increasing the amplitude of electrical signals is called as amplifier. But what is a differential amplifier? A differential amplifier is a type of electronics amplifier that amplifies the difference between two input voltage but suppresses any voltage common to the inputs. It is an analog circuit with the two inputs V in minus and V in plus and one output V out, in which the output is ideally proportional to the difference between the two input voltage, that is V out equal to A into V in plus minus V in minus, where A is the gain of the amplifier. Okay, so have you got that one? What is a differential amplifier? The name itself gives you. It amplifies the difference between the two input signal voltage given at the input. Okay. This is a general block diagram of a differential amplifier. See that one, we are giving two inputs V1 and V2. That amplifier amplifies the difference and we are getting the output V0 as A into V1 minus V2. Okay, A is the gain of the amplifier. This is the circuit diagram of the general circuit diagram of a differential amplifier. See that one, we are taking two common emitter amplifier. They are connected back to back. It consists of two transistors Q1 and Q2 that have identical characteristics. That is, they have to be made from same set of transistors. They share common positive supply, that is VCC is common between that both RC1 and RC2, and they are having common emitter resistor, that both emitters are connected to the emitter resistor RE to the negative voltage V supply, negative supply VE. Okay. Configurations of the differential amplifier, there are four basic configurations are there in the differential amplifier. They are single input unbalanced output, single input balanced output, dual input unbalanced output, dual input balanced output. What is that single input unbalanced output means? See the diagram, it shows that one. We are giving only one input. See that one in the input side. In the input side we are having one resistor. Okay, sorry, one source voltage. See here this one voltage source is connected at the input. Only one input is given here, and the other side it is grounded. So there is only one input. So it is called as single input. See that one, where we are taking the output. Generally in the previous diagram, if you see that one, we are taking the output between the both collectors. Okay, but here we are taking the output at the only one output. Okay, only one collector output. Since we are taking only one collector output, it is called as unbalanced output. Okay, unbalanced output will contain unnecessary DC content as it is the DC coupled amplifier. Therefore, this configuration should follow by a level of transistor circuit. The effect of input voltage V in 1 coupled to the transistor Q2 via the resistor, that is Q1. Okay. Next, we are going to discuss about single input balanced output. See that one, we are giving only one input and we are not providing another one input, that is it is grounded, and we are taking output between both collectors. Okay, so we are taking one end of the CRO is connected one end of the CRO is connected in the RC1, another end is connected between that RC2. So we are taking output between two collectors. This will give us more amplified version of the output as it is combining the effect of both transistors. There won't be any unnecessary DC current in the balanced output, as the DC currents in both outputs get cancelled with each other. That is, V0 will be given by V01 minus V02. So both DC any DC output in present in this signal will be eliminated by this way. Okay. Next, dual input unbalanced output. Here we are giving two inputs. Both Q1 and Q2 are given with the two sources, V in 1 and V in 2. But we are taking output from only one transistor through RC2. If you are taking that output from only one transistor, then it is called as unbalanced output. Since we are giving two inputs, both the inputs are given, it is called as dual input. Since you are giving unbalanced output, there will be some DC components. So you have to give another one transistor circuit to avoid the DC output. Okay, next we are going to discuss dual input balanced output. Here we are giving two inputs and we are taking the output between two transistors. So we are getting that balanced output. So there will be no DC components present there. And the output V0 can be given as AD into V in 1 minus V in 2. And the input voltage V in 1, if V in 1 equal to V in 2, then obviously the output should be 0. Okay. Here AD is given as the differential gain of the amplifier, and V in 1 is the input voltage given at the transistor 1, and V in 2 is the input voltage given at the transistor 2. Okay, let me start with DC analysis. When you are going for DC analysis, we have to find out the values of VCEQ and ICQ. Okay, so for DC analysis, you have to open circuit the capacitors, and if any AC source is there, means that should be eliminated. So we are open circuit the capacitors, and you are getting that one, the source resistance RS1. Assume RS1 equal to RS2, that is equal to RS, and your Q1 is identical with the Q2, and your emitter resistance RE1 equal to RE2, and that is equal to RE. Okay, and your RC1 equal to RC2, that is equal to RC, and we are taking that VCC is equal to the VE, except that negative. Okay, symbol. So we have to find that ICQ value. For that one, apply KVL to the input side, and we are getting the IB value. From the IB value, you are having that one. So these are all the derivation parts. From the IB value, you will get that VCE equal to VCC plus VBE minus ICRC. And similarly, your IB value will be equal to IE by beta. So we have obtained the value of IB, and your IC value is equal to VE minus VBE divided by 2 times of RE. Okay, so we have obtained the value of IC and we have obtained the value of VCE. Okay, IC equal to VE minus VBE divided by 2 times RE, and your VCE equal to VCC plus VBE minus ICRC. Next, we have to find the differential input resistance. That RI1 is given by VR1 divided by V in 1 divided by IB1, and that RI1 is after derivation you can obtain that RI1 is equal to 2 times of beta RE dash. Okay, and your similarly RI2 can be given as 2 times beta of RE dash, and the output resistance R01 equal to R02, that is equal to RC. Okay, let me start with that common mode rejection ratio. What is common mode rejection ratio? It is the ability of the differential amplifier to reject the common mode signals. Okay, a differential amplifier is said to be a common mode when same signal is applied between both inputs. Okay, and the expected output will be 0. That is, ideally common mode gain should be 0. The CMRR can be given as it's the ratio of differential gain to the common mode gain. It is the ability of a differential amplifier to reject the common mode signal, and CMRR equal to modulus of AD by AC. The unit of CMRR is decibels. So CMRR can be given as 20 log AD by AC. Okay, next we are going for the small signal analysis of differential amplifier. Using this small signal analysis, we have to obtain the gain of the amplifier. For that one, let me start with that small signal equivalent circuit of the differential amplifier. Since both the sides you are having common emitter circuit, this is the small signal equivalent circuit. From this one, we have to find the value of V pi 1 and V pi 2, and then we are applying VE value. And from that one, V0 can be given as from one side, that is from Q2, you can write that V0 equal to Vc2, that is equal to minus Gm into R pi divided by V pi 2 by R pi into Rc. By substituting the values of V pi 2 by R pi, you will get that V0 in terms of beta times Rc into Vb2 minus Ve divided by R pi plus Rb. And instead of VE, you have to substitute the value that already we have arrived from that. So from that one, you can obtain that after simplification, we are having V0 will be equal to minus beta times Rc into Vb2 minus Vb1 divided by 2 into R pi plus R beta. Okay. So from that one, you can obtain that differential voltage gain AD equal to V0 by Vd. Vd is the differential voltage, that is V in 1 minus V in 2. Okay. So here V in 1 is Vb1 and V in 2 is Vb2. So you can write that one. So remove, instead of Vd, you can write that minus of Vb2 minus Vb1. Then you will get that AD equal to beta times Rc divided by 2 into R pi plus Rb. And that is if Rb equal to 0, then you are having that AD will be equal to Gm into Rc divided by 2. Okay, this is the differential gain equation. Then we have to go for the common mode gain. So for that one, we have Vb1 which is equal to Vcm, that is common mode signal is applied between the input and output. So we are getting that Vb1 will be equal to Vcm plus Vd by 2 and Vb2 will be equal to Vcm minus Vd by 2. So substituting the values of Vb1 and Vb2 in the equation V0, you are getting that one V0 will be equal to beta times Rc divided by 2 into R pi plus Rb into Vd minus Vcm Gm into Rc divided by 1 plus 2 times 1 plus beta R0 divided by R pi plus Rb into Vcm. Okay, this is our V0. And if you are taking that one beta Rc by 2 times R pi plus Rb as AD, and we can take that another term Gm Rc, that is multiplied term of Vcm, can be considered as ACM. Okay. So from that one, ACM can be given as minus GMRC divided by 1 plus 2 into 1 plus beta R0 divided by R pi. That is our ACM value. Or you can write that one minus IQ into RC divided by 2 times VT, the whole divided by 1 plus beta R0 IQ divided by VT by beta. Okay. Next, we have to find out the common mode rejection ratio. As you know that one, CMRR or rho is given by AD by ACM, modulus of AD by ACM. We should not consider the negative symbol here. That can be given as 1 by 2 into 1 plus beta into R0 IQ divided by VT by beta. This is the common mode rejection ratio. So if you are asked to derive the common mode rejection ratio, you have to obtain AD, ACM, then you have to go for CMRR. If you are asked to obtain that AC analysis of the input signal, you have to arrive at AD and ACM. Okay. Next, we are going to discuss that DC transfer characteristics. The DC transfer characteristics of a differential amplifier is a graph of differential input Vd against the currents IC1 and IC2. Why we are going for this means it is very useful in identifying the range of the differential input voltage over which the circuit operation is in linear region. Okay, the basic dual input balanced output differential amplifier circuit is considered here, and we know that one, this is the circuit. And to obtain the transfer characteristics, following assumptions are made. The current source circuit used in the current IQ has infinite input resistance. The assumption we have made, and the second assumption we have made is the source resistance Rs in the base of the transistor Q1, Q2 are neglected. and then the output resistance of each transistor is infinite. The assumptions are valid for low frequency, large signals only. For a transistor, we can write this equation for its collector current IC equal to Is into e power VBE divided by VT, where Is is the reverse saturation current and VB is the base emitter voltage and VT is the voltage equivalent of temperature. Thus, for two transistors, we can write the equation IC1 as Is into e power VBE1 divided by VT and IC2 equal to Is into e power VBE2 divided by VT. Okay, where IS1 equal to IS2 equal to Is. And then neglecting the base currents and assuming IQ is an ideal constant current source, then we have IQ equal to IC1 plus IC2. That IQ equal to Is into substitute that IC1 value and IC2 value, you are getting that IQ equal to Is into e power VBE1 divided by VT plus e power VBE2 divided by VT. And taking the ratio of IC1 to IQ, we are getting that one Is e power VBE1 divided by VT the whole divided by Is into e power VBE1 by VT plus e power VBE2 by VT. If you are simplifying this one, we are getting that 1 by IC1 by IQ equal to 1 by 1 plus e power VBE2 minus VBE1 divided by VT. Similarly, we have IC2 divided by IQ equal to 1 by 1 plus e power minus VBE2 minus VBE1 divided by VT. And from this one, we had VBE1 minus VBE2 equal to VD. And you can write that IC1 equal to IQ divided by 1 plus e power minus VD by VT, and IC2 can be written as IQ divided by 1 plus e power VD by V2. So substitute various values for VD and obtain the values of IC1 and IC2. You can have that DC transfer characteristics for the differential amplifier. This is the DC transfer characteristics of a BJT drawn for IC1 by IQ and IC2 by IQ. So with that, we had discussed all the characteristics of a differential amplifier, DC transfer characteristics, common mode amplification, differential mode amplification and its common mode current gain, differential mode current gain, and that CMRR so far. With that, we have completed the entire second unit. Thank you.